So today is a little different from the rest of the lectures. We're going to have a Q&A session, but there's no questions being asked because they already were all asked on Piazza. Since there's a fairly large class, we obviously won't have time to get to everyone's question. So we selected a number of questions that just sort of we felt were topical, or we felt incorporated ideas from multiple other questions, or ones that got multiple upvotes in the stream. There were a lot of ones we really liked that we didn't get a chance to include just because we had to limit them at some point, and we weren't quite sure how to respond to them. So these were some interesting combination of both interesting questions we thought. Seems like a lot of people were focusing on the right thing, on the same thing, and we had a response we thought was a little bit interesting. So I guess we can take it away from there. They're broken up into a few different categories. So we're going to talk about general AI, safety and ethics, about machine learning and deep learning, and then finally about game theory. And then we have some other miscellaneous ones at the end if we have time.
And by the way, we encourage you guys to also, you can follow up with additional questions.
Yeah.
So it would be nice if there is an additional discussion, like around our answers. Another interesting anecdote is of the 67 questions, 32 of them had either deep learning or neural network. So it's pretty obvious what you guys are interested in, and we'll talk about that as well, but also about some other topics. Okay, so the first topic is general AI. We actually have only one question on this, but there were a couple of questions. I think we just pulled out one. There were a couple of other related ones. This was also one of the few non-anonymous questions. It was by Mikil, I think. So essentially the question is, what's the roadmap from the current state of AI to a general intelligence kind of machine that can pass a much more general Turing test that can interact in many ways. Okay, so the short answer is nobody really knows, but there are, I think, a few interesting things we can say here. So I think it makes sense to start by thinking about what there is now that is closer to general AI. One example that I really like, I talked about it in the intro lecture, is this work from DeepMind about learning to play Atari games. So there, I mentioned this briefly in the first lecture. So you had, one algorithm based on deep reinforcement learning that gets as input feedback, which is only pixels on the screen and the rewards in the game. And based on that, this one algorithm was able to learn 50 vastly different Atari games. So this is, it's just really cool. It's, I think, a nice example of something that seems like it's going on the way to more general intelligence, but of course, still very far from being general intelligence. Another example that I want to give is a bad example is personal assistants like Cortana or Siri. So these are things where it looks like it's going in the direction of we have this intelligent assistant that will help us in different ways, but actually I think the way these things work is that companies identify use cases that the current technology can already solve, and then they just build these specific use cases into the personal assistant. So I think here it's misleading to think these things are getting more intelligent, but it's, in a sense, it's not actually going in the right direction. It's more by specific use cases that we know how to solve. Let's just add them in. Okay, so what would a roadmap actually look like? So one point that I think is a lot of people are not aware of is that in Turing's paper about the Turing test that he called the imitation game, he actually also talked about what a roadmap would look like towards general intelligence. And so his main idea was building this child machine, which would basically learn in this very kindergarten type environment, and learn skills over time. The thing is that Turing, at the time, people weren't thinking about machine learning, so thinking about rule-based AI. And Turing actually estimated that to build a child machine, it would take 60 programmers 50 years. So that's 6 million man-hours to build the code required to start learning in this kindergarten type environment. So it's sort of a nice direction, but a very different view of AI from what we have today. But this is actually related to a relatively recent proposal from Facebook AI Research, so a bunch of relatively prominent machine learning people. And they were saying, they also like this idea of a simulated kindergarten environment where we have a learner that is learning from a teacher. And it's a similar idea of building from very basic skills. So the idea is we'll have a teacher that is actually scripted, so it's not really intelligent. And then the teacher will, and the learner will be like, a combination of existing or future machine learning algorithms, but not something that takes 6 million man-hours to build, something a lot more basic. But the idea is this learner will start by acquiring very basic language skills and then expand on them to get more advanced language skills, then maybe interact with the person and learn even more, and so on, and build its skills in many different directions. But really the main challenges are first this idea of storing skills in long-term memory and composing skills in order to learn more advanced skills. So this is something we don't know how to do well today and would have to be done. And the second, which is something that machine learning is not good at today, is learning from relatively few examples. So you're interacting with the teacher, but it's not big data. The teacher will give you some examples. There's some limited interaction, which is like in a human environment. And then the idea is that the learner will really have to do well on this pretty limited amount of data. So that's another big challenge for machine learning that you would have to overcome. And the last comment about this is that, an interesting point is that it actually goes against a lot of wisdom built in AI over many years. So in the 70s, people talked about building agents and teaching agents in simulated environments that are very simple. Like an example is the Blocks World environment, that dates back to the 1970s. But in the past, these things didn't really scale up because we didn't have machine learning. So people basically, did this rule-based AI. It worked well in these very well-defined environments, but didn't scale up to the real world. And the idea is that now things are different because machine learning will allow the simple agent to generalize beyond the simple environment and then, acquire more skills as you deploy it in the real world.
Okay. So I'm going to take a little bit more negative viewpoint of this idea. Not negative in the sense that this is never going to happen, but negative in the sense that this is really an important question to think about right now. So I'm going to borrow an analogy from Andrew Ng on this, and he uses this analogy, and I think it's actually kind of apt. He says that thinking about a roadmap for general AI is a lot like thinking about how we're going to colonize Alpha Centauri. So it's actually not a bad thing to think about as an exercise, right? It's good to think about. I'm happy there are people thinking about how to colonize Alpha Centauri. It's probably a good thing, and you can kind of think about steps to get there too. Like first, we're going to develop a certain type of solar sail that can carry us this. Then we have to solve this problem, this problem, this problem. But it's speculative to a degree where I'm not sure if it's going to have any bearing on the actual trajectory we end up following to do these things, right? And so I think that there's a danger in thinking about general AI when we really don't understand intelligence enough right now to think about building a machine that can solve that Turing test. And these examples of sort of building a simulated kindergarten, I think, they're interesting, but they don't speak to any of the obvious failure modes that we would encounter when we actually did this endeavor. And they only work because we haven't kind of tried them. We sort of haven't tried them yet. We haven't followed through on the entire path. And I don't think there's really that much value in trying to follow through on those things yet. I think the path that we're going to achieve more and more degrees of intelligence is actually much more along the routes that we are going. Hopefully at some point, starting to understand our own mental processes better. I think a lot of the work in neuroscience here may eventually, it's nowhere close to the point where we could really understand anything about the brain, but I think it's worth thinking about how we're going to understand the brain to do that. And I think that these directions that have more immediate payoffs, in addition to potential long-term views of AI, are going to ultimately be the more fruitful directions, and those are the ones that I am personally more excited about. And when it comes to current AI, which is what I actually work in, I'm more personally excited about ways that AI can actually play a role in the next, say, 5 to 10 years, instead of the next no one knows how long, because we have no direct path to actually getting to any of these questions.
Any additional comments? Okay, so let's talk, we want to talk a bit about safety and ethics. There were quite a few questions about this, and we sort of pooled several of them together on each slide. You'll see actually on the next two slides every time there's going to be a question that will seem unrelated at first, but then we'll see how it's related after we talk about the answer to the first questions. So these questions, the first two are generally about ethical issues in AI. So what are the ethical issues, and do we need to address them? So we wanted to talk about two ethical issues. One about the ethics of self-driving cars, and the second is bias in machine learning. So bias in machine learning will be the topic of the next sequence of questions. But that's just, as a specific example, I think it's fun to think about the ethics of self-driving cars. And again, like Zico has quite a different viewpoint from mine. So let me start by giving sort of my viewpoint. So, there's one really interesting question that people have been talking about a lot recently, and it's basically the trolley, a reincarnation of the classic trolley problem, which is a classic problem in philosophy. So in the self-driving car context, the question is basically as follows. The car has some catastrophic brake failure, and it's going to be in an accident. But then because it's a self-driving car and has these advanced perception and processing capabilities, it can actually make an informed decision about which bad event it prefers to occur. So for example, it could be the case that it can go straight, hit a wall, and kill its passengers, or it can swerve and run over a bunch of pedestrians and kill them. And the question is, which one of these options should the car do? So there's actually a website that I want to show you from a team at MIT called moralmachine.com. So that's asking people a sequence of questions like this. And this is a specific example. So here, the car can either go straight and hit the wall and kill the passengers, and then it will kill 2 women, 1 large man, and 1 man, and they're in the car. Or it can swerve, kill the pedestrians, who are in this case passing on a green light. They might also be passing on a red light, which could be relevant. And then the pedestrians are 2 female athletes, 1 man and 1 male athlete. So which would you prefer? Like, do you prefer to do this or that? So you can choose this, it will give us another option, and so on. So this website asks people a series of questions like this, and they actually collected like 20 million votes from over 3 million people expressing opinions on this. But it's still very far from telling us like how do we build an algorithm that would answer these questions. So I just want to tell you briefly about some work that we've been doing actually with Ritesh, and in collaboration with Iyad, who built this website, and Pradeep Ravikumar, who's a professor at MLD here. So the starting point is the data from this website, and the idea is to use social choice in order to make these decisions. So the thing is, we have millions of voters who cast these votes, and each one was shown only very specific alternatives. Kill these people or kill these people. In practice, of course, the car would encounter very different alternatives, but because these alternatives have features, we can actually use these pairwise comparisons to learn a random utility model of the type we talked about a few weeks ago. So specifically, we're using the Thurston model, the one with the normal distribution. So now we can learn a random utility model for each voter that participated in these experiments, millions of people. And the idea is that when the car encounters a dilemma, in real time, what we do is we store all of these preferences that we learned, and we want to aggregate these preferences over the current alternatives using a voting rule. Okay? And the fact that because we have the features and we have the random utility models, it's essentially asking all of these millions of voters in real time, what would you do if you were facing the current dilemma, and then aggregating this using social choice approaches. So that's the approach we're working on. I think it's nice in the sense that it gives a very concrete answer to this question of, how would you build an algorithm that makes these ethical decisions? Basically, the approach that's implicit here is ask people, and really the trick is, we can ask people about completely different things and learn their preferences about new alternatives that we might encounter. So that's sort of the short description of this idea. So how is this related to the third question here? The third question says, it's a very interesting separate question, which is AI is this black box. We don't really understand the outputs of neural networks, for example. So how can we deal with ethics in AI if we don't understand these things? So I think like the kind of approach I just discussed gives a partial answer to this, which is, self-driving cars in general, of course, a lot of them are built on machine learning, including things that are not very transparent. But the idea would be when you encounter an ethical dilemma like this, you basically give control to this different algorithm that would make the ethical decision. So it doesn't necessarily have to be built into the usual algorithms. You can basically delegate control to a special purpose algorithm to make the ethical decision. So Zico has the
Okay.
completely different viewpoint.
Hide my slides there. I don't want to give her. Hide the comments. I don't want to give
Oh,
her
sorry.
too much of that. Okay, so I want to provide a little. So I want to start off by saying I think that the directions of sort of this kind of the intersection of looking at ethics and sort of crowdsourced ethics is a fantastic direction. I do want to provide a little bit of a reality check though when it comes to self-driving cars in particular. So there's this notion, I think, that's pervading the media that somehow self-driving cars need to handle this scenario of deciding between killing one person and killing another person. And that this is kind of a dilemma because normally we sort of hand this off to the driver, but in a self-driving car, it's someone that kind of would have to think of it beforehand. And what do you do beforehand? How does the programmer do this, right? So I would argue to you that there are actual ethical issues, of course, that involve self-driving cars, and this is not one of them. A real issue involves self-driving cars. And what I mean by this is the following. So there are going to be, when we develop self-driving cars, and this is, I think, this is going to happen relatively soon, I mean, relative in the large scale of AI, right? Somewhat in the near-term future, this likely will happen. And there are going to be lots of deaths caused by self-driving cars. Right? They are going to. There are going to be cases where they kill someone, and not just like it couldn't be avoided. Like they're going to kill someone, and they're going to kill people. I would submit that approximately 0% of those deaths are going to be a case like what you saw there. The deaths that are going to be caused by self-driving cars are overwhelmingly going to be because of two things. They're going to be, first of all, because of outside factors. So another human makes a mistake and kills themselves, essentially. They jump in front of a self-driving car, right? That's not really the car's mistake. The mistakes the car are going to make are going to be about bugs in the code. Or more specific, and I'm using that term kind of colloquially, right? But they're going to be about things that were misspecified in the algorithm. It's not going to be about the programmer ahead of time thinking about two alternatives and killing one person instead of another. It's going to be about them never thinking of the scenario or having some error in how they process their data, and that's what's going to cause deaths. And we've already seen this. The Tesla car that was on autopilot that killed someone, I mean, you're required to have your hands on it. This person was not doing that. But that person, the vision system failed. It didn't see a big car. It thought this big truck in front of it was the blue sky, and so it just drove into this truck. That's gonna be the ethical issues, really. I mean, to me, that's the key ethical question. There is, how do we know how to trust these systems when they are truly autonomous? Right now, we're kind of okay handing it off to Tesla or handing it off to the users and saying, look, this is an autopilot, but that means you have to be paying attention the entire time, and you're still at fault if you crash. When we actually transition away from this, and there are genuine errors and bugs that programmers make in building these systems, and they cause deaths, that's the ethical dilemma that I'm most interested in, or if not directly, then I think is the most relevant to think about. And I do worry that this sort of notion of playing against, playing the trolley car problem and dressing it up a little bit kind of distracts from that much more prevalent reality. And so I don't think it's wrong to focus on that too, but I think we have to accept and understand that is a fun philosophical question to talk about over drinks, but it's not going to be the core in my mind of what ethics and the ethics of self-driving cars involve.
Yeah, so they just quickly respond. So I mean, we did talk about this, and Zico knows my opinion. And so one point is, the kind of approach I think we both realize is more general than the trolley problem. Right. So this is sort of a case study. The nice thing about the trolley problem is we have this massive data, right? But you could apply the same crowdsourcing kind of approach to any ethical problem in AI, as long as you get millions of people to tell you their preferences in that domain. And I think a second point is that there's also a matter of what people perceive. So if people perceive this to be an important problem and think this is an issue when they buy a self-driving car, one could argue this is a question that needs to be addressed just because it's something people care about, even though technically it may not be a big issue.
I'll also get back to later about how you might judge, when we talk about explainability and interpretability of models, I'll talk about how you might judge whether or not a car is safe. Because I think that's also an important question, right? How do we know when to hand over the reins to our cars and completely take the human out of the loop? That's an important question too. So, all right.
Cool. Okay, so the second ethical question is more specifically about bias in machine learning. So this is something that has also been like in the media a lot lately, and people, I mean, it's an issue a lot of people are thinking about. So the kind of issues are, for example, there's a lot of evidence that people can be shown different ads, for example, based on race or gender. So there's evidence of black people being shown ads for like worse credit cards or things like that. So this is something that is a big problem, and the question is how to fix this. So the question was, what is in our opinion the right way to approach this problem? So I want to tell you, so before we talk about question 2 here, and we'll see how this relates, I want to tell you about like a specific approach that was suggested and a specific thing that I have thought about, and just as like one fun kind of approach to this problem. So here's an approach suggested by Dwork et al. In like a 2012 paper. So it's a theory paper with some really interesting ideas. So the way they think about the problem is you have a space of individuals. And so each individual is a point here that is defined by different features like gender, it can be anything, age and so on. It can even be race, education and so on. And then there's another space of outcomes. So let's think about the advertising example specifically. So these are ads. And actually we'll think about distributions over outcomes. So the idea is, we have some function that says for this individual with these characteristics, they're going to be shown this particular distribution over advertisements. And this individual, or this profile, will be shown this distribution over outcomes or ads. Now, in addition, there are distance functions on these spaces. So this space has some distance function capital D that can be a standard distance function on distributions, like total variation distance. So this is not very interesting. The interesting part is that this space also has a distance function. And this is really the tricky part of the model. So the idea is that this distance function captures what is acceptable in terms of, when can we distinguish between two individuals based on their characteristics. So for example, two people who are exactly the same except for their race, their distance should be very small or zero, right? Because we as society think we shouldn't be able to determine the outcomes based on race, or even in some cases based on gender. In some cases, it could be okay to take gender into account. There are things specific to men and women, but in other cases, we may not want to take gender into account. So this function is this mysterious function, and this we're going to come back to this in a minute. But it's a big question how you would come up with such a function that takes this stuff into account. And then the optimization problem is minimize some loss. So we want to come out, we want to find a mapping F that minimizes some measure of loss, which is, if you take Google's perspective, it's like how much are we not classifying people or showing them the right ads, the one that would maximize revenue. And then the interesting part is they do it subject to a Lipschitz constraint that says something like the distance between, so for all individuals x and y, the distance between f of x and f of y should be at most some k times the small d between x and y. So this says if two individuals are close, according to the mysterious function d, they should also get similar distributions over outcomes. So this is a really cool idea. For particular distance functions, capital D, this is actually a linear program, so this problem is pretty easy. The big shortcoming of this model is how in the world would you come up with this function small d, the distance function sort of captures when we can discriminate. So here's an approach I would like to suggest. I think it's a nice idea, but I don't know what to do with it. So if you guys have any ideas, I'm happy to hear them. So the idea is the following. Let's assume that every person x has a utility function u sub x for different outcomes. And this utility function is something we can elicit from people. So we can ask people would you like to see this ad? Would you like to see this ad? And we can actually learn a utility function for people over ads, for example. Now, and it could be the case that different people actually have different preferences for different ads, right? If I'm poor, maybe I do want to see like a credit card that is aimed at like, people like me. So the idea would be, we still want to minimize loss like before, but we're going to capture fairness using the idea of envy-freeness that we talked about when we talked about integer programming. So in this context, what it would mean is that the utility, so for every x and y, the utility of x for his outcome f of x will be at least the utility of x for y's outcome f of y. Right, so this is this classic notion of fairness, and it's just saying, okay, let's ask people for their utilities, and using that we can just plug it into this to this like classic notion of fairness, and immediately get like a much more concrete optimization problem. And by the way, this would also be a linear program. So this is again, it keeps the computational tractability, but to me it seems much more concrete in terms of how you would come up with this fairness constraint, in practice. So that's sort of my 2 cents on this question. And if you guys have any ideas later, let me know. Like, so this is like a nice statement, but now what do you prove about it, or what do you do with it? So that's an idea.
Yeah.
Can I ask a little about this thing? So we are saying that my utility for the ad that I see is the best one among all possible outcomes that I can have.
Not necessarily. So f of x is a distribution over ads.
Yeah,
So,
sure.
right. So this doesn't mean you're getting your favorite possible ad. You're getting some distribution over ads, and I'm also getting a distribution over ads. We can say for distribution, my we look at the expected utility for the distribution under the utility function.
Yeah.
And what I want to say is, so it could be the case that I'm not being mapped to my favorite ad, but I still like my distribution better than yours.
So among all possible distributions that could be shown to different people, my distribution is the best one.
No. So every person is shown a specific distribution,
Yeah, sure.
right? And we're only comparing like the distribution shown to other people. So
Yeah, exactly. So among all possible distributions that actually shown to all different people, mine is the best.
defined by the function f.
Yeah. Okay.
Take it away.
All right.
Now the part
Ariel's
you've
gonna
already-
go take a nap for a while.
The part you've already
Okay, so there's going to be 3 classes of questions. I tried to group them into 3. People have a lot of questions about deep learning and machine learning, and I'm largely grouping them into 3 approaches. Which I use examples, but I'm going to also highlight kind of the general question I've seen here. So these first questions were largely about: is there any way we can start to formalize the selection of hyperparameters or model architectures in neural networks? Right. So a key, I guess, motivating factor for when I introduced neural networks was saying that most machine learning, it treats the feature mapping as a fixed thing you have to specify as an architecture, as an architect of the system. And then once you've specified those features, you just train the system with whatever method you want. And that's how classical machine learning works. But look at these nice neural networks, you can learn the features, right? You can actually learn the features from data. And that was kind of one of the ways I motivated deep learning. So the natural question is, can we just push this sort of, get one more level of meta in this process, right? And now just say, well, why don't, it looks like it's kind of a pain to specify all these 128 layer architectures. Why don't we just learn the neural network architecture and sort of go from there? And so I think it's from a high level, it's not a bad idea. And maybe in the next revolution of deep learning, once this excitement fades and we can't do this, then the next people will say, oh, well, why don't we just learn the structure? By then we'll have ways of doing it better, and it'll be the next huge wave in AI. But I don't think this is going to happen quite like this in the next, I would say, at least 5 years. And this is actually going to get to be, I'm going to sort of hash on this point a lot in the next few slides. But the point I want to make is deep learning architectures are currently the way in which, when we use a neural network, we impose structure on the problem. So if you have an image problem, I know it seems obvious at this point because everyone uses convolutions, but the idea of using a convolutional architecture itself is really a way of imposing structure on your problem, right? Because we want to say, okay, look, I know that convolutions have these properties. They are invariant to some amount of translation, this kind of stuff. You know, if you slide the same weights over the image, you get something here, same as there. That really is a property of images that we felt was a good property to exhibit in our models. And it's sort of become, at this point, kind of old hat on images, so they become this sort of black box themselves. But this fundamental idea is actually really important if you go about applying neural networks elsewhere. So if you have some system where maybe some of your features or some of the inputs to the system are very similar to other inputs, say maybe you have two sensors that are the same sensor, they just placed at different locations on some system, you should think about ways to constrain your architecture that takes into account this dependence, right? So maybe you put like a tied weight system where you use the same weights to process the first sensor as the second one. Again, this sounds kind of obvious, but the point is that the idea that like the core idea of deep learning, as I see it, is sort of compositional differentiable units you can kind of chain together. And the way we accomplish great things with this is we chain them together in good ways that sort of address the problem structure that we want to address. And in fact, if you look at deep learning research, if you don't really know the field, it looks like just a mess of people just trying random things. And so you might just think, well, you know, why don't we just automate that trying random things? But really there is all the intelligence of the system is going into designing these architectures in a way that preserves the problem structure that we want. And so we are along, and that still does require a lot of intelligence. It's a little step away from engineering the actual features themselves, but it still requires that we apply some sort of high-level understanding in designing these architectures. Not at every stage. I mean, there certainly are cases where you just add a few more layers of a generic type and it kind of works a little bit better, but for the most part, the vast amount of improvements in deep learning are due to designing the right architecture. One thing I find is that unlike what people I think often think of, which is just sort of neural networks are these pure black boxes, I think actually that the things we learn in sort of academic machine learning are just starting to become more and more important when it comes to deep learning. So things like how do we constrain the weights to be of a certain, to have certain characteristics where they're shared across certain different inputs regions. How do we tune a loss function, right? How do we pick a loss function that actually optimizes what we want to optimize or tries to optimize what we want to optimize? These are questions which are actually much easier to solve with deep learning architectures because you have this differentiability and you can just sort of push everything through these derivatives. It makes the things that we learn about machine learning and how to apply machine learning more important, not less important. And so I think that we are a long way from being able to take a new problem and have the box itself figure out the right architecture, the right hyperparameters, everything for this deep learning architecture. Any questions before I go to the next one? So I think, yeah, this paradigm of connecting together multiple differentiable units is actually the crux of deep learning, not convolutional networks or not more layers and not neural networks and nonlinear functions. It's compose things together that try to solve your problem and then optimize that whole compositional structure. This actually relates to the next one too. So the other question we got a few times was sort of why don't we use more complex optimization techniques in deep learning? So we learned fun things like the simplex method, right? Which despite it actually being very old still, was substantially more complex than gradient descent, right? And so it seems kind of sad. And so we asked some questions about are there more general and powerful optimization techniques that could be brought to bear on deep learning? And secondly, why do we seem to be throwing out constraints when it comes to deep learning systems, right? We talk only about unconstrained problems now, whereas in optimization we focus so much on constrained optimization. Why are we okay just throwing it out entirely? And the answer here is actually well, the first answer to the first one is why don't we use more complex optimization techniques? So certainly there have been a slow and steady development of more complex algorithms that are not just stochastic gradient descent. So the current favorite by citation count is an algorithm called ADAM, which is essentially, you can do it a few different ways, but essentially is a normalized version of stochastic gradient descent, but it does some clever normalization, and it seems to just work a little bit better. So there is some work in algorithmic techniques to do that, but it still is a really simple algorithm. The truth on the first one is that despite its simplicity, it really these algorithms, these sort of stochastic gradient descent algorithms, seem to be the best and seem to be better than what we can do is trying to attach more complexity into the system. So there's been a lot of work in trying to do second order optimization in neural networks, and it doesn't work. At all. I mean, people always try to come and say, okay, yeah, they show their example on a paper and so that it works better. Then everyone else tries it on their problem, and it doesn't work at all. So we have had a really hard time trying to apply more complex, genuinely more complex methods and have them uniformly work better than simple gradient methods, where, again, simple gradient is not quite that simple. You have a little bit of momentum, you sort of a little bit of history in your gradient step directions, but that kind of seems to be the state of the art. There doesn't seem to be that much benefit currently in more complex methods. That being said, this is very much an active research area. So Elad Hazan from Princeton just came a few weeks ago and gave a talk on second order methods for neural networks, and then at the end said, oh, and they don't really work in practice, but we're trying to make them work more. It's recorded but not public, so it's actually okay. So we're trying, but we aren't there yet. And the second one also asked, I think, a similar thing about why don't we think about constraints? For example, couldn't we constrain the weights in a network and use this to impose structure on the problem? And I would actually say that this one we are already doing, because things like convolution or things like tied weights are exactly just constraints on the weights. They tend to be equality constraints, right? Saying that this set of weights is the same as these ones here, or you apply the same set of processes on this chain as in this chain. But again, getting back to my previous point, I think it is actually exactly the constraints we impose on the architectures that make deep learning interesting and that make it work, frankly. Convolutions are a huge constraint on the allowable space of weights as you would have if you had a fully connected network, right? So that is a constrained optimization problem. We just don't formulate it that way because it's a little harder to optimize. We formulate it as we're applying the same thing, and we're going to use a chain rule to differentiate this thing and kind of sum up over all the paths that these weights follow. But we are constraining weights when we talk about these things. I think it's really important to think about deep learning as a way of providing for a constrained architecture applied to a problem, and all the discussion about how we might be able to do better if we apply inequality constraints to equality constraints, maybe, but it seems like we're doing pretty well with what we have in terms of the constraints that we do apply. Another good example actually is the softmax function, which is basically you take the last output of a neural network, you exponentiate the values, and you divide by their sum. That is, in some sense, a projection of that last layer onto the simplex, right? The sum of a positive set of numbers that sum to 1. In optimization, we typically write simplex constraints as it has to lie in the simplex. We write it in terms of, right? I'll use the whiteboard here, but if we want to write I didn't use this at all during the whole class, so I'm a novice at it. But if we want to have a set of x in Rn such that the sum of all x is equal to 1 and the xi's are all positive, we write this as a set of convex constraints. But if we want to do it in a neural network, if we want to have a unit that has this constraint in a neural network, we just call it a softmax function. And we say that xi is equal to the exponential of some previous one, I'll just call it yi, divided by the sum over all I of x of yi. And this has the same constraints as this one. It's just done in a way that's differentiable and which is a little bit easier to differentiate through. So a lot of the constraints that we think about, a lot of ways when we think about constraints and convex optimizations. Oh, by the way, this is not a convex version of it, though, right? So if you can't write that in a convex program because x is not a convex function of y now. But a lot of the constraints that we wrote with these convex procedures in convex optimization, they really do carry over. They just are they're just being carried over in a subtle way when we talk about deep learning architectures. And by the way, these kind of things sort of appear everywhere, and that's really how we encode constraints in a lot of deep learning frameworks, because they're differentiable and because we can easily kind of back propagate through them. Okay, thoughts there? Comments? We're gonna breeze through all these questions. We're gonna be done in no time. Okay, so the last one in deep learning. I think this is another common criticism of deep learning, is to say, well, the models that deep learning creates are not interpretable, right? We have no idea why, it says this picture of a dog, but why not say it's a dog? And in fact, you can trick it really easily by like adding a little bit of noise. Basically what you do is you take the gradient of the loss with respect to the input image. You take a very small step in that direction, and you add some noise which is imperceptible to a human, but which changes the classification of the image as far as the system is concerned. So you see in these examples of like you have an image, another image looks the same. The first image is a dog; it looks the same to us, but the thing says, the neural network says, oh, this is a panda bear or something like that, right? I think that. This is actually not necessarily a bad thing, right? There are optical illusions that fool humans too, so this is just like the optical illusion for neural networks, right? There's going to be like books of these things someday, and the neural networks are going to read them and say, oh, that's amazing, it's a panda, but it looks the same as a the robot's reading one of these books of adversarial images, right? So these things are definitely a problem from a standpoint of some of these systems. But again, playing devil's advocate, as I've liked to this whole session, I like to do that when we talk discussions. Oftentimes, people sort of phrase the understandability of these systems as a reason not to use them or somehow not to trust them. Right? We can't trust these systems because they are understandable to us. And I think this is kind of an odd requirement to have, especially because we don't understand our own brains at all, yet we're more than willing to trust it, right, when it comes to making decisions and these kind of things. So what I would argue, I think there are 2 points here, because I do think there's a lot of work that needs to be done and that can be done in making AI more explainable, and there's a lot of good reasons to do it. But as a high-level point, I do want to make the point. I do want to offer the argument that the reason why we trust human explanation is not some sort of fundamental. It's not some fundamental kind of philosophical, ethical, moral reason. It's an empirical reason. We trust sort of human judgment because we've seen time and time again it seems to be pretty reasonable, right? We sort of see these things work. We see humans making arguments, they seem to work, and we sort of follow along with that. This is maybe sort of ignoring the fact of whether things like mathematics exist in the true world or not, or whether they're just a human conception. But let's ignore that. I think a lot of human judgment is trusted based upon the fact that it appears to just work again and again. In fact, getting back to autonomous cars, the reason why we trust humans as drivers is that they tend to work pretty well as drivers. Not as well as they should, unfortunately, but tend to work pretty well. And so the guarantee, so when it comes to like autonomous cars or any system where these are kind of making life and death decisions, I think the example here was like health diagnosis in autonomous cars, the way we're going to trust them, in my mind, is not going to be some formal proof that they are correct. It is incredibly hard to formally verify the real world, right? When you have a camera system that's predicting what's going to happen there, how do you formally verify that? You can't show it all possible images. It's really, really hard to know how to verify, truly guarantee that the things are going to work in the unconstrained kind of full setting when they have complete autonomy. The way we're going to trust them is they're just going to start working better and better than humans, and we're going to kind of get okay with it after a while. That, I think, is why we trust humans to drive cars. They were seen as really dangerous when they first came onto the scene. Cars were, and they are. They're horribly dangerous. But we're sort of okay trading that convenience, trading that danger for a little bit of convenience. And once we see empirically again and again that these things work, we are going to be willing, again, to trade a little bit of danger, actually in this case less danger, because we're already in more danger, but we're going to trade a little bit of some risk of death for the convenience of taking a ride in Thomas' car where I don't have to actually pay attention as I'm driving. I can do some work or I can sleep or whatever else, right? Now, so I think it's important, my view on this is it's almost going to be purely an empirical one, and it's going to come from seeing these things deployed, seeing them drive how many millions of miles before they have an accident. That's going to be the metric that determines safety, not kind of a formal metric. Again, opinion here, but that is what I believe. Now, having said that, I do think that there is a lot to be said about trusting neural networks in a lot of cases, especially in cases where we already have something that works pretty well. So a lot of like automation processes are like this, right? We actually have pretty good models of a system. We run some optimization in it. It kind of works well. There's probably some things you could tweak, and then some intern comes in and says, well, I know reinforcement learning. I want to replace the entire process chain you have with reinforcement learning because it'll work better, right? And look, I have a simulation here, and I'm showing you that it does work better, and so that's great. Now, I think there we are at a little bit of an impasse here, because it is true that people, when we talk about sort of designing rules for how we operate machines and how we operate our processes or how we operate computers, right? People do want to see a little bit more than just a complete black box where it just takes in, states and outputs actions, right? We want to know a little bit about, well, why is it telling me, trade all my money here away from a system? Why isn't it? Why should I do that? Should I just trust it? I don't know. People want to have a little bit of, and this is not a matter of sort of. This isn't a matter of kind of whether or not we're going to use the system at all, but it is a matter of whether we use one system that seems to work pretty well versus another one that may work better hypothetically, but we don't really know. So I do think that there is some need to kind of expose the internals or the decision-making process of these algorithms in a more understandable way. So some of the work that my group does, including people here, is think about ways in which we can code more concrete optimization problems and decision-making problems within the structure of a neural network, such that the network kind of predicts what it needs to predict about, say, like how the state's going to evolve, but then we still solve the ultimate decision-making problem with an optimization problem that's understandable to a human after that fact. And there's some subtleties there that actually are needed to make this whole thing trainable in a single fashion, so a single kind of process as opposed to having just two separate modules, but we're sort of working on things like that. The other point I'll make is I actually think some of the more ingenious research out there is about ways to take existing neural networks and try to gain insight into them. So one very cool trick people do with image classifiers is the following. So if I give you an image of a bear and the neural network says it's a bear, how do you know if it's seeing a little like bear cartoon in the corner and finding that, or like hallucinating a bear in the trees or something like that and saying, okay, I see a bear up there, but you just missed the bear right in front of you. And the way people do this is they actually take a little, they black out parts of the image. They take like a little window that's black and slide it over the whole image, and then look at the classification when you black out a portion of it, right? And so what you do is you slide this window over the whole image. You see where you most decrease the probability of it being a bear, or whatever it was classified as, and that part of the image probably is the part that caused it to be a bear. So this is a very simple idea, right? You're just sort of masking the image in a way that kind of reveals what the algorithm is actually doing. But I like these ideas because what they do is they actually think about how can we take an existing system. Let's not worry about trying to constrain the system to somehow be interpretable on its own. Let's take an existing system and try to modify it or inspect it in a way that actually reveals its processes more directly. And I think actually this is oftentimes how we kind of get information about our own opinions in our own brains, right? We formulate a trolley problem because it's a concrete example about dealing with a moral ethical dilemma where we don't have to, set up someone to actually die or not, and see what people actually do. So I think it's really valuable to think about how we can inspect models or even design them. But I'm also high on just the inspection properties as well. How can we inspect them to understand what decisions they're making actually are? And this is going to be also, I think, more and more an issue as these things do cause problems, and you do have an autonomous car that kills someone, you're going to need to, at least after the fact, figure out why that happened. And a lot of the times, this kind of analysis and inspection is going to be the way that we actually determine these kind of root causes. So I think this is going to be an important area and field going forward. All right. Next up. I'll take a nap for a while.
Yeah, this is the part you've actually been waiting for. Game theory and social. We actually don't have that long. We have like 25 minutes.
Yeah, no, I know.
Okay, I was deliberating. I actually realized I skipped a question before. Let me go back to it briefly because I think it's interesting. Yeah, so here, I was talking about this idea of using NV-freeness for bias in machine learning. I actually forgot to tie it back to the second question I put on the slide, which are, look especially at like after the first sentence, laws aren't made by majority vote, they're guided by moral, ethical, and humanitarian standards. Thus, even population data might want a certain inhumane law to pass, it cannot. So this is sort of taking the viewpoint that we can't actually ask people or look at data to solve problems because there are some things that are some basic moral principles that we can't just ask people about. So I think actually the two examples that I talked about here take the opposite viewpoint. Like I disagree with this point, and I think like in many cases it does make sense to ask people like what they would do. That gives us a really good baseline for ethical principles, at least for working algorithms that would make reasonable ethical decisions. The viewpoint here is closer to this viewpoint of there exists this function small d, right, which is the one that captures the true morals of this problem. So this is the viewpoint that is closer to the one expressed in this question. So I just wanted to make this point. Okay, game theory. So here are the first two questions. I wanted to use them as opportunities to recap some material that we talked about and slightly expand on it. So this one is saying, well, we treated game theory and voting theory as two completely separate topics. Is the research that ties them together in terms of developing voting systems that provide incentives to be honest? So first I wanted to remind you guys that we did talk in the second social choice lecture, we talked about manipulation in elections. So we talked about the Gilbert-Satterthwaite theorem and using complexity to circumvent manipulation. But I wanted to say more broadly, there is a lot of work in social choice, at the intersection of social choice and game theory. So just to mention two things that are directly related to what we talked about. When we talked about the Gilbert-Satterthwaite theorem, so we said, okay, the theorem says there's no voting rule that is non-dictatorial and strategy-proof, basically, as long as you have three alternatives and it's onto. In fact, as long as the range is of size at least 3. But one question people have asked is, okay, if instead of a deterministic voting rule, we allow randomization, can we do better? So this dates back to a paper by Gibbard in '77. And essentially what he's saying there is to define strategy proofness, you actually need to define a utility function because we want to talk about your expected utility for some, under a randomized rule for distribution over alternatives. And then you can define this notion of strategy proofness for randomized rules that basically says, you have some utility function. Your loss is going to be determined by the expected utility. And telling the truth means ranking the alternatives in a way that's consistent with your utility for the alternatives. So are there, we want rules where you can never gain by ranking in a way that is not consistent with your utility. So let me give you an example of a rule like this. So take choose two alternatives uniformly at random, like a pair of alternatives. And then of these two alternatives, take the one that has more voters preferring it to the other alternative. Okay, so I choose X and Y at random, and I choose X if a majority prefers X to Y, and Y if a majority prefers Y to X. So this is strategy proof because, for the same reason that majority voting is strategy proof. Like once X and Y were selected, I have no control over that. If I prefer X to Y, but Y was selected, I couldn't have gained by putting Y above X. That only helps Y. So this rule, if you think about it, actually amounts to just choosing alternatives with probability proportional to their Copeland score. Okay, so this is like a randomized rule, a pretty natural one, and it is actually strategy proof. And similarly, if you take a voting rule like Borda, and you select alternatives with probability proportional to their Bordas score, that would be strategy proof according to the strong definition. But what Gibbard showed in 77 is a characterization of strategy proof randomized rules that is actually very restrictive. So the kind of things I talked about now are essentially the only things you can do, the only kinds of voting rules that would be strategy proof, in a very hand-wavy sense. So, so there's a pretty good understanding, for example, of what we can get, voting rules that are actually strategy proof if you allow randomization. Now, another topic that's related to stuff we talked about worst case complexity as a barrier to manipulation. But the thing is, I didn't really mention this in the lecture, but worst case complexity is a pretty weak barrier to manipulation. Because what it says is there will be cases, there will be instances where it's hard for the manipulator to find out how to cast a vote to get a better outcome. But it could be the case that usually it's actually easy to manipulate the rule. So this is not actually gives you any guarantees in practice. And there is quite a bit of work thinking more about average case notions of manipulation. It's including stuff that I've worked on. But most of the results right now are pretty limited. So they're basically saying the worst case results, saying formally that the worst case results don't actually give you guarantees in practice. And it's a very, very interesting open problem, extremely interesting, to actually be able to design a voting rule that is reasonable and where manipulation would be hard on average. Okay, so that's a big, super interesting open problem. Any other questions about this? Okay. So another question just that I want to use also as an opportunity to recap. How to apply game theory and social choice to artificial intelligence? Can you give us an example? So I think one thing that's implicit in this question is the definition of artificial intelligence, that we will get to that in the last slide if we have time. But let me just remind you of some of the examples we talked about and give a couple more examples. So, we talked about things like applying game theory to poker, right? Extensive form games, imperfect information sets, and so on with applications to poker. I think that's something a lot of people intuitively view as AI, right? It's like one of the, playing traditional games is one of the paradigmatic examples of AI for a long time. Another example that we gave for game theory is security games. So here again, it's a very concrete real-world example. It has a lot of connections to learning, for example. A lot of the work today is about how to learn the utilities of the adversary in order to improve these algorithms. Of course, it has many connections to the type of optimization paradigms that we talked about. So it has many, many connections to different areas of AI. But then you can argue, is a program that helps people make intelligent decisions using all of these tools, is that AI? I would say definitely yes, but that depends on your definition of AI, which again we will revisit soon. For social choice, one example that we talked about is thinking about these cases where we have objective opinions and we want to pinpoint the ground truth. So I think of this as a problem that's closely related to ML. And in my view, the big difference is that we don't have features for the alternatives. So in some sense, it's not a case where we try to learn from data, and really the crucial missing thing is the features. It's more like, okay, we have these rankings, for example, over alternatives, but we don't know anything about these alternatives. Then what do you do in that case in order to be able to pinpoint the ground truth? Right. So this also had many machine learning connections, and I think you can think of it as a different viewpoint on a machine learning problem. So these are some examples that we talked about. I just gave you the example of using social choice for ethics and self-driving cars. So that would be another example. Just to give you another example, off the top of my head, it's something that a faculty candidate gave a talk on a few weeks ago. So again, going back to autonomous cars, something people are thinking about is now, you may have on the road both autonomous cars and people. And these different entities are interacting. So you can think of this interaction as a game between the car and the person. And it's basically, the goal is to design control strategies or control algorithms for the car that take into account how the human would respond to what the car is doing. So the way they're modeling this, she is from Berkeley and doing work with people from Berkeley, is as a Stackelberg game. So using a lot of the approaches that we talked about when we talked about security games. And of course, there's a big element here of learning what the utility function of the person would be as well. So that's kind of a nice example, also very relevant now as we have more self-driving cars on the road. Another similar example that is sort of becoming timely now is when you think about personal assistants like Cortana and Siri actually buying stuff for you online. So we just said that's not genuine or not going to general AI in a sense, but it is. You can think of this as a multi-agent system with software agents that are interacting through these marketplaces. And the really interesting thing about this is that this, in some sense, like tools like game theory are even more relevant to think about a system like that than to analyze human behavior, right? Because these are agents that we actually design, and we design them to be rational, and we design them with certain utility functions that we know. So here, these are cases where game theory actually works better than for the purpose for which it was originally designed, which is thinking about human interaction. So these are sort of some of the really exciting things that are happening right now in terms of how game theory is being used in AI. So I want to just make one more philosophical point. It's a lot more hand-wavy, but I think kind of a cool point to make. So, in terms of how you can fundamentally view game theory as AI. So game theory, one of its chief goals is to think about what is rational and to distill rational behavior. Think about what rational agents would do. And, rationality, I guess, is something which we can view as sort of a sufficient condition for intelligence. Maybe that's a strong statement, but at least like an agent that behaves rationally is something that we are likely to perceive as being intelligent. And you could make the argument, I don't want to completely support this argument, but I think it's an argument that's interesting to think about, that when you have a system that is populated by these rational agents and they're interacting according to the rules of game theory, because you have all of this rationality going on, when you view the system as a whole, you can think of the system as being intelligent. So you can think of the intelligence as being captured on the system level when the rules of interaction are governed by game theory. So this is an argument that would say, game theory is fundamentally part of AI in that sense. So again, I think there are counter-arguments. It's a very hand-wavy argument, but interesting nevertheless. Okay, so a somewhat more concrete algorithmic question is the following. So let me read the question. We've seen that AI is doing well recently in some games such as Go or poker, which are tasks which do not need immediate response within seconds or milliseconds. However, AI is not doing so well in real-time tasks, such as driving or playing real-time games. Is this gap in performance caused by the limited computation time of real-time tasks, only such that it could be narrowed as we develop hardwares that are more powerful? Or there's also a fundamental difference between real-time tasks and those that are not so? We need different approaches to solve them. I actually really like this question. It's like a really thoughtful question. So I think a couple of thoughts. One is it's not about the response time. So to give you like a concrete example, if you think about Limit Texas Hold'em Poker, so this is something that has been essentially solved, which means there's basically a lookup table where you can, at every step, you can look at the table and it will give you your strategy. So that means that can actually be played instantaneously. Okay, so it's not really about, that's not the obstacle. So it's not that really the fundamental difference is that in poker, we can have some time to think. In this variant of poker, which is a real world variant, you can actually act instantaneously. That's not the big issue. So, focusing on games, maybe Zico can talk later about driving, but focusing on games, if you think about StarCraft, for example, what's the fundamental difference between poker and StarCraft? So, StarCraft is a continuous time game, and I think the main issue is that the state space is huge. So in particular, you're just making, so first of all, you have many decisions you can take at any point. In an advanced stage in the game, you have all of these units you can move around in any direction. You can build units at your base, you can build buildings and so on. So the action space is infinite because you can move in any direction, but also there are all of these different types of actions, and you need to make decisions all the time because of the continuous time. So the state space is just, I don't even know how to estimate it. Like it's insanely huge. So, these days we actually have tools to deal with continuous action spaces. So for example, for no limit poker, where you can bid any amount, right? You can think of the action space as being continuous space. What people have found is that you can actually discretize this pretty well, and you can do these abstractions where you say, all of these states are actually pretty close to each other, so I don't need to reason about all of them separately. That's called the lossy abstraction. So I may lose in terms of being suboptimal, but it's, all of these things are pretty similar. So this is stuff that works really well and we know how to deal with. But really with StarCraft, the challenge is this like crazy huge state space, and how in the world do you deal with that? So this is something people are working on. Like it's not hopeless. But it's but it is like a big challenge. Okay, but I think that's really the main difference: the size of the fact that continuous time games give rise to this huge, enormous state space. Okay, so last question about game theory: would game theory take into account empathy or altruism in real-world decision making? So this is actually something game theory has really struggled with over the years. I guess the first answer is that if you're very, very careful about defining the utility function, you can basically build anything into a utility function. So for example, if somebody cares about, if we're dividing money and I get benefit from how much money you guys are getting, we can build that into my utility function. So that's always like a possibility, but it's basically cheating. I think something that game theorists have looked at quite a bit are games where you do see altruism. So a nice example of this is the public goods game that works as follows. Each of us gets some amount of dollars, like $10. And then each of us is asked to decide how many dollars they want to keep to themselves and how many dollars they want to give to some public project. And the idea is that every dollar that you give to the public project gets multiplied by some factor that is larger than 1 but smaller than the number of players. And then those dollars get divided among all of the players. So essentially the idea is that for every dollar you give to the public project, you yourself get less than $1, but in terms of social welfare, like all of the players get more than $1 together, because it gets multiplied. So to maximize social welfare, everybody should give like all of their money to the public project, and then would get like a lot more as all of this money is divided. But selfishly, of course, like because for every dollar I give, I'm getting less than $1 back. Selfishly, I shouldn't give, like it's a dominant strategy not to give any money in a one-shot public goods game. Nevertheless, when this is played, people do give, they keep some money and give some money. So this kind of thing is something that game theory really struggles to explain. And commonly, the models people use to try to explain this is repeated games. So saying, it's not actually one-shot interaction. What people have in mind, because we're used to this, is a repeated interaction. In a repeated interaction, if you're interacting with somebody who sees that, that you're not giving any money to the public project, over time, they're not going to give any money either. And you can also see this in the prisoner's dilemma, where if somebody is defecting, and like your opponent sees you're defecting, they would start defecting as well, but then everybody would lose. So all of these phenomena can be explained in a repeated game. And there is, of course, a lot of formal work saying, these kind of things are actually equilibria in the repeated game. So that's sort of the approach game theorists have taken to try to reason about something like altruism. Empathy, I don't know. Any questions about game theory? Okay, so we'll just have like 3 final miscellaneous questions.
I might skip to the last one. Well, I wanted to address the last one, but I'll mention just a few random ones. So there was one comment on sort of I would call it like AI. I don't want to put words in the person's mouth, but like AI cooperative creativity with machines, right? Can you build tools such that we can be more creative with humans can be more creative with the machine? And I think so. And actually, the example that I'll give I don't want to spend too much time talking about this because it's definitely not my area. I don't really know anything about this, but Photoshop's a great example of this, right? Where Photoshop actually is a tool that lets people that ordinarily couldn't do things create art and edit pictures in ways that they just couldn't do otherwise. And actually, a lot of you may have been seeing a lot of sort of recent press in ML or recent sort of news stories in ML and deep learning have to do with these being able to transform an image that looks like from a horse to a zebra and things like this, and like from daytime to nighttime and stuff like this. And actually, I see this as being incredibly valuable if we can provide a way for humans to sort of give high-level input. I am not a very artistic person. I cannot use Photoshop at all, actually, other than sort of for basic purposes, because I'm just not very. I just don't really. I'm not when it comes to at least painting art. I'm very unartistic, and so I think that allowing people. The concept of machine learning is you specify kind of what you want rather than how you want it done. And I think actually that same thing applies to art in a lot of cases. I think I'm a much better critic than I am of an actual artist, right? I could see when I draw something it's actually really bad, right? I can do that, and as long as you can kind of tell what you want, or maybe point to examples of what you want, I think actually these techniques actually will let you have a Photoshop where I say, give it a picture, and I say, okay, I want this picture to look like something else from here and something like this and there, and designing the interface lets you do that. I think it's actually a really cool problem. So I'm looking forward to Photoshop in 10 more years. I think it'll actually be something I can do something with, maybe, if they put a good interface on it at least. So another one which I actually think a lot about is about education. So not in terms of what we saw here applying AI to education, but how do we teach people about AI? This is obviously something that we think about a lot because we're designing the curriculum for AI, and this is one incarnation of that. So I think that, and I think that there was more to this question, but there was also some more follow-up about, given that there's 10 courses in machine learning at CMU, it seems to be, how do you as a student kind of structure and learn this topic when it seems like there's just an infinite amount of stuff to learn? So the first thing I would say is that the current techniques actually aren't that complicated. They're actually relatively straightforward. I mean, if you want to learn deep learning, you can probably do it in a semester at least, if you sort of invest your full time doing it, right? And though it's probably actually less true for other areas, there are actually more complex other areas, quite a bit more than deep learning, because there's actual theory and stuff behind it. It isn't actually as hard as you might seem. So I think part of what sort of makes it difficult is people see these fields kind of from afar, and there seems just like there's all this ongoing literature kind of going on, and it's easy to miss the bigger picture. Whereas people that know the field, what their primary sort of ability is the ability to sort of look at a paper and know what it's about right away, and then just sort of say, okay, this paper fits into this compartment here, and they can go back and find out details if they want. So I would like to try to capture more of that in the education framework for AI as a whole, and that's what we sort of strive to do here. Kind of give you a broad overview, but at the same time also some details in certain areas that let you sort of take a broad view of the field and say, okay, I'm going to read this new paper, and I don't really understand it, but I can compartmentalize it in a certain place and put it here. And I think teaching that aspect is actually going to be really important. And then you can go and sort of, we'll never be able to stay with the true cutting edge of research, of course, but you can go and kind of build from there. But of course, how you educate people in an advanced field is a concept that a question that's been around for a very, very long time. So the last one. Maybe I'll let Ariel speak first about this, but it has to do with the definition of AI. So you've all taken an AI course now, and this person was asking sort of what is AI in more or less words. So the question is, the definition of AI is becoming more and more subtle. So it seems like people talk about AI when they mean machine learning, computer vision, game theory, social choice, everything, right? It seems like everything is AI. What is this a problem? And how is the sort of usage and coverage of AI changing? you can give your thoughts on it first.
Yeah, I think here, like, I have the more cynical view, and Zico has the more optimistic view for a change, or the more positive view. Yeah, so I think one, or at least like one argument that could be made is that these definitions of scientific fields are very much a sociological thing. So there are these scientific communities that evolve over time, and the definitions basically depend on what people in a certain community are working on. It's like the two big AI conferences are called Triple AI and InchGuy, and the two broadest AI conferences, let's say, and biggest. And the most cynical definition would be AI is everything that is published in Triple AI and InchGuy. So that is a valid definition, but of course, like probably not what the person who was asking the question was looking for. But I just want to give you one nice example. So like a week ago, we were talking about changing the constrained elective for undergrads. There's like an applications constrained elective, changing the name from applications to an AI actually constrained elective. And the question was what to call this constrained elective. So one proposal was, I was advocating just AI, but one proposal was computational intelligence, which sounds like another word for AI. But then if you look at Wikipedia, what is computational intelligence, it will tell you it's often used as a synonym for soft computing, which sounds pretty bad, but what is soft computing? So some people think of it as actually machine learning. So it's just, all of these words that all are basically the same, and it's just about, different communities that use different words for different things. They don't have any intrinsic meaning. So I really think like it's really about more the sociology of science than like any, that there's actually a definition for each of these terms. Regarding coverage, so just to give you two examples, game theory was something that until the 90s most people didn't see as AI. And then there was like a big push to, in AI, in these communities, working on game theory and social choice and topics like that. And today, almost everybody views it as very much a part of AI. So this is something that is, wasn't a part of AI 20 years ago, and now is very much a part of AI. A more recent change, I think, optimization has always been, some parts of optimization were parts of AI. But for example, recently things like convex optimization is something that, you can see many papers on convex optimization being published in AI conferences, whereas you wouldn't see that a few years ago. So this is like an example of a topic that is becoming part of AI sociologically and in practice, and wasn't a few years ago.
So my view on this is that AI sort of is the study of all things that relate to some aspects of intelligence that are done on computers, which is broad enough to cover all those things, but I think we should embrace that. It is a very broad term. It means a lot of different things to different people. The field is constantly changing, but I see no reason to constrain ourselves in the definition that it can't be all of these things. And we should become a point where, though there are, of course, going to exist distinctions between other fields and CS, of course, I don't think those are going away anytime soon. We should be happy about the fact that AI is robotics, and AI is computer vision, and AI is machine learning, and all these things. It's a useful designation of a field of studies that are trying to replicate some notion or some aspects of what we think of as intelligence. It's a major goal, but I think we should embrace the broad definition to the point where I'm okay calling almost everything I do research-wise and a lot of the stuff that I do, even outside of research, kind of work in AI. All right, so we're over time now. Thanks everyone very much, and we're looking forward to seeing everyone at the video session. I guess a week from Friday, right?
Yep.
All right.